Start something with me.
Stood stuff up with me about Folgers versus Folgers. But I will not lower myself.
I'm not sure Folgers is coffee.
You're not sure Folgers is coffee?
What kind of coffee do you drink? Dr. Justin's like a Starbucks person.
No.
He's a black coffee type guy.
I drink Caribou coffee. That's what I typically drink. It's based in Minnesota.
It's good.
Yeah, it is stuff that I think.
Folgers is farmer's coffee.
Huh?
Folgers is farmer's coffee. That's what every farmer I've ever met in my life drinks every morning.
Every time I think about Folgers coffee, I think about the old commercials about, well, Jim never drinks coffee at home, but then it would be airplane where he pukes. Funny, Jim never vomits at home. That's all I can think of every time I hear about Folgers. So my brain doesn't work right. It's fine. All right. That's what happens. All right. So let's look at this particular example problem. Hopefully this will help to. We'll do a couple of example problems. I want to make sure I get a couple of example problems down so you can see what you need to do for homework problems. For a couple of these with conditional. So this one gives you the marginal for x and a conditional PDF for y given x. Okay? So even before I read what the rest of the problem asks me to do, if I'm given the marginal for x and I'm given the conditional for y given x, I should be able to recover the joint PDF. Right? Because we know that from our formula, we know that the conditional PDF is equal to the joint PDF divided by the marginal, right? So if I rearrange that equation, we'll know that the joint PDF is the product of the marginal and the conditional, which should remind you of the probability formula, right? This looks like the probability of x and y. This is the probability of x, and then the probability of y given x. That is the probability. That's our conditional probability formula we had way back when, right? It's the same concept. All right. The reason why we have to do this a little bit differently when we do these conditional density functions is I don't want to try to think of this particular formula. I don't want to think of trying to put in a value for x in here to start the formula because, again, the probability that I actually equal a particular value is 0, right? So when I do the conditional density function, I need to worry about these in terms of marginal ideas, not the probability that x is actually equal to a number, because that's going to be 0 no matter what for a continuous, right? Right. So in this case, I can recover the joint PDF by just multiplying these two things together. We'll take the 3x squared and multiply it by the k times y over x squared and get 3 times k times y when we cancel our x's. Now, I'm probably going to need to go about and figure out what my k is, although I'm not sure I really care since it has it in the problem. We could figure out the k pretty easily. Either we integrate this over all the y's and set it equal to 1 and solve for your k, okay? Or integrate this over your entire space, set it equal to 1 and solve for k. We've certainly done problems like that, right? Yeah? Okay. All right. So we've recovered the joint, which now can help you figure out other types of problems. We should also know what the support is. So in this case, what are your x values run from? 0 to 1. It tells you right up at the top, right? We agree? So I know my x's go from 0 to 1. What do the y's run from? 0 to 5x. So I would need to graph the line y equals 5x. So it would go up here to 5, and we'd be looking at that triangle. So that would be the other piece of information that might be useful as we're going through and trying to solve problems after recovering the joint PDF. One of your problems in the homework asks you to compute a probability one of the variables. I think it's time. Right? It tells you the claim size, tells you conditional probability for time given claim size. And it asks you to find the probability of the time is past a certain amount. I think it's very, very helpful if you can graph your support, be able to figure out the piece you need to integrate over for your probability. At least I find that helpful. And I'm not a visual person, and I think graphing it helps. Yeah, Morgan.
So is that the graph of your joint?
That's the graph of the joint support, yeah.
Okay.
And I got my axis from this part, and I got the line y equals 5x from this part, and I knew to shade below because it was y was less than 5x. So I used those two pieces of information together to get me the support. So far, so good? Okay. All right, so now it wants us to figure out, now I can read the problem. Because the first thing I did, I didn't even care what the problem said. I saw marginal, I saw conditional, I got joint. Okay? Because I figure at some point I'm going to need to use it anyway. Okay? Now the second part says find the conditional of x given y. So basically, it's kind of like those Bayes problems that we did, right? When we had y given x, we converted it to a statement about x given y. So it's kind of like the analog of that, just in the context of continuous distributions and doing PDFs. It's the same kind of thing though, right? Because when we do Bayes problems, we have to know how to flip from one to the other, right? So in this case, to find the conditional, I'll call it H, the conditional of x given y, what do I need to find? Well, I need to know the joint, certainly. And what do we need to divide by in that case? The marginal of y, the given part, right? So I need to figure out this piece. So how do I find the marginal of y? Okay, so yeah, I need to integrate over all the x's. So let me pull up a different color here. So I need to integrate over x's for a given y. I need to integrate this way, right? Okay. So what are my bounds for my x's then? Y over 5 to 1? Because again, what was the equation of this line up here? That was a y equals 5x, right? So that's where the y over 5 comes from, solving for x. And then we integrate the joint PDF, which was 3ky, and we'll do this dx. Right? Notice that there are no x's in the PDF that we're integrating, so this is just going to be 3ky times 1 minus y over 5. Right? I can just basically I can take the 3ky, pull it out in front, and I just get x, and I plug in the endpoints. So now to figure out your conditional, we just need to divide. We have 3ky on top, 3ky times 1 minus y over 5 on bottom. The 3ky's cancel, and if you multiply top and bottom by 5, you get 5 over 1, or excuse me, 5 over 5 minus y, which is b. What's interesting about this one for the multiple choice, which I don't really care that it was multiple choice, you can throw out a lot of answers right away. For example, especially if you know your support, right? What's the biggest that y can get? 5, which means my y naught piece in there is going to be probably less than 5. What's that make part C? If I put in numbers that are less than 5. I'll make them negative, right? Which can't happen for a marginal or a conditional a PDF in general, right? Same thing, the same problem with D, isn't it? My x could get as big as 1. It's going to be negative again, isn't it, if it gets too big? So it can't be D either. E's just the joint, probably not that one. And A says 1, I think. So it's probably not that one either. So if you were just guessing on this one, you would guess B. Assuming you understood what the support and the joint PDF look like.
We had a problem like this. We run out every reason it can't be.
Sure. You can reason through all of that. This one okay? Okay. See if we can do one more here that, I don't know if I have one copied in here or not, so I may just need to pull it out of the book. Let's look at, if I can get to it. Let's look at 4.3-16. Is that the one I want to do? No, we're going to do that one. I may need to do another one if I don't. All right, so this one says that X is uniform on 0, 1, and Y, given X, is uniform on 0x. So the first part asks you to find the conditional, Y given X. All right. So they tell you that it's uniform, right? In this case. So finding the actual distribution isn't too difficult, or the actual PDF of that isn't too difficult, because if we have a uniform distribution, what is the PDF, if you know the endpoints? 1 over B minus A. In this case, this is just going to be 1 over X. And that's again because it's uniform, right? And we also know, I didn't ask for the joint yet. I think that's part C. Part C asks for the joint PDF. Well, if I have the joint, what else do I need besides the conditional? I need the marginal, right? So we need the marginal of X. Because we have the Y given X, I need the marginal for X too, right? But again, what do they tell us about the distribution of X? It's normal, right? Or not normal, uniform. I can't say the right word. It's uniform on 0, 1. Sorry. So if it's uniform on 0, 1, what is the marginal going to be?
1.
It's 1, right? So what does that mean the joint's going to be?
1 over X times 1.
Good. Now again, one of the things that we will need to know is what the support is. So again, if I think about graphing this off to the side, apparently smallly, but that's okay. What are your X's run through? 0 to 1. And what do your Y's run through? 0 to X. So I need to graph the line Y equals X. And it goes from 0 to X, right? So we'll be shading down here. Morgan.
Explain A. How you got 1 over X.
It's uniform on 0 to X. Remember your PDF for a uniform distribution is 1 over B minus A. So it's X minus 0. Marshall, do you have a question?
I was about that same thing.
Oh, that's the same thing. That's where it comes from. Are we okay with the support here? Everybody's so happy. Wonderful. That's what I like to hear. What's that?
Why is it under?
Because it says from 0 to X for the Y given X. So we're going this way. Okay. And then D asks you to find the marginal of X. Well, that's not difficult to do. Or not the marginal of X. Conditional of X given Y. Oh, no, I'm sorry. It says find the marginal of Y. I can't read. Sorry. That's why I try to make copies of these and stick them in here so I don't have to look at the book and go back and forth. Find the marginal with respect to y. Yeah, again, not too difficult because I need to figure out bounds for the x for a given y, right? Got to integrate horizontally. We agree? So what are your bounds for x's then? Y to 1, right? Of 1 over x dx. So now there really is an antiderivative here to do. Natural log. So we'll get negative natural log of y when we're done. Because we'll get natural log of 1, which is 0. Minus natural log of y.
So your marginal is going to be negative?
No. Y is less than 1, so it's going to be positive.
I see.
Yep, that's why. I know, it tricked you. It like to be tricky. If you like it without if you actually don't want the negative in there, you can always flip it up as an exponent, make it 1 over y. Do it that way. I mean, it looks weird because you have a negative in there, but you have to remember the y is less than 1. This okay? The idea okay? Now, in some of these problems, your marginals end up being piecewise defined functions, and your conditionals end up being piecewise defined functions. I think that happened in the one I gave you. Yeah.
A quick question about that on the homework. Sorry. When they're piecewise, I kind of just solved them like individually. I never actually wrote it as one complete function. Do you want it written as that, or kind of circle each of them?
As long as you tell me for what pieces those are.
Yeah.
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 Yep, that's fine.
I mean, I like to write stuff out cleanly on my.
I don't know that.
All right, is that okay? Were there other questions about anything homework? Because I'm going to talk a little bit about test. Does this going through this type of problem help with the homework?
Yes.
Okay. Also, some of them ask you, I guess one of the things I should have said is, some of them ask you to do expected value. So for example, this one actually for part B asked for the expected value of y given x. Okay, so this is, you do the expected value the same way. We're going to integrate over all the y's of your y times your PDF and integrate it with respect to y. Now, in this case, your y is ranged from what? 0 to x, right? It's still going to have an x in it. So it's going to go from 0 to x for that computation. So we'll have the integral from 0 to x of y times 1 over x dy. Now again, x is a constant as far as y is concerned, so this becomes y squared over 2 times the 1 over x. Right? And we get x over 2. Now, again, is this a surprise? Did I even need to go through all this work to figure? For this particular one, did I need to go through this work? No. Why not? Why not? Because it's uniform, right? We already know what the distribution of y given x is. If you have uniform from A to B, what is the expected value of uniform A to B? It's B plus A over 2, right? You have to add, it's the average of the endpoints, right? 0 plus x over 2 is x over 2, right? I went through it because by definition, that's what the expected value is. But if you know what the distribution is, then you know what the mean of that distribution is, there's no point in going through the work. I know it's uniform on 0 to x, so its expected value is x over 2. You don't have to go through the work to do it. Because we did all of the work when we derived those formulas to start with. It didn't matter what A and B were. Right? So 0 is playing the role of A, X is playing the role of B here. That makes sense? Now, in your homework problem, I think if you did your margin, if you did your expected value, if you did your conditional PDF correctly, you have 3 pieces. And the one you had for homework, for your conditional of Y given X, if I remember correctly, there was 1, 2, 3 pieces, depending on if X is between 0 and 2, 2 and 4, and 4 and 6, right? So that means that when you do your expected value, it's also going to have 3 pieces. A piece from 0 to 2, bless you, a piece from 2 to 4, and a piece from 4 to 6, where you'll compute your expected value here the same way we just did above. Integrate over your X, integrate over all your Y's, Y times the conditional. Okay? Now, in that problem, why did you have a piecewise defined function? You had those different sections, right? You had a section, I don't have this graphed exactly right, because this should be this way, right? There was a piece that way that was vertical, and then a piece this way that was vertical. So let me try again. Make this a little bit better. So let's go this way and this way and make this 4. How's that? Better? Scale's not great, but better than it was. Right? Okay. The reason why is because in this region, you've got those 2 bounding curves for Y. In this region, or interval I should say, you've got those 2 bounding curves for Y. In this interval, you've got those 2 bounding curves for Y. Right? Do you agree? So when you do this expected value of Y piece here, you're going to do for 0 to 2, for 0 to 2, what will your bounds for your integral be? 0 to X, right? Of your Y times your conditional, right? Because those are your bounds for your Y. Okay? From 2 to 4, what will your bounds be?
X minus 2 to X.
Okay, so X minus 2 to X, yeah. And the last ones? X minus 2 to 4. And again, your expected value will be a piecewise function of X. The reason why it's piecewise is because it matters what piece you're on to get your bounds. Does that make sense? Yeah.
That's the X minus 2 on the 4.
Yep, this is X minus 2. Yep. But again, we use the same principles for doing expected value. We take variable times PDF. In this case, though, your answer should involve x's because it depends on the x. The whole idea. Any other questions about anything before I start talking about tests? I don't want to wake Michael up.
I'm awake. Would have brought you some coffee from the cafe.
All right. So, where did we start? Section 3.5, is that right?
Yeah.
All right, so, and then 3.6 was your normal distribution. I'll talk about it in a second. Gamma and chi-squared, those are two that you'll need to be able to write down. The PDF, the mean, the variance, the moment generating function.
Can we be reminded as to what they're about?
No, I'm not going to tell you.
We're going to get a table. For,
I'm going to give you the chi-squared table and give you the normal distribution table. Because I will want you to use those to solve problems. If you don't have them, you're going to have a lot of memorizing to do. All right, so your gamma PDF is x to the alpha minus 1 e to the x over theta gamma of... Oh, did I not say the negative?
Yeah, so I was looking at the screen, I was writing it down.
Oh, I thought I said negative, but I may have missed the negative sign when I said it. I wrote it. All right. Gamma of alpha, theta to the alpha. Yeah. The mean, whoa, that was fun. The mean, alpha theta, the variance, alpha theta squared, the moment generating function, 1 over 1 minus theta t to the alpha. You should have memorized exponential from the last test. If you let alpha equal 1, that's the exponential. Right? Okay. So that's gamma chi-squared with r degrees of freedom is a gamma distribution. Okay? X to the r over 2 minus 1 e to the minus x over 2 gamma of r over 2 2 to the r over 2. That is a gamma distribution, right? If your theta is 2 and your r is an integer, positive integer, gamma chi-squared of r is that gamma distribution. This is just a subset of the gamma. Just like the exponential is a subset of the gamma, right? Yeah, Chelsea. R over 2
minus 1.
Minus of 1 is up in the exponent, yeah.
So it's the quantity of r divided by 2, and that all minus 1, right?
Correct, yes. What's wrong? Did I miss something?
What's the symbol there?
This one? This one?
No. The one over.
This one?
Yeah.
That's a 2.
Oh, okay, because I always wrote the alphas as 2. Okay.
Actually, with the gamma, whatever's in parentheses, so just take 1 minus that, or subtract 1 from that, and then take that factorial.
If it's an integer, yeah.
Yeah.
Yeah, so I'll go through that here in just a second. So this is gamma where the theta is 2. So this is 2 times r over 2, which would just be r for your mean. And your variance would be 2 squared times r over 2, which gives me 2r. And your moment generating function will be 1 over 1 minus 2t to the r over 2. You had a homework problem where it was a gamma distribution, and I told you that at that point it was okay to use Excel to find the answer, but if you recognize the chi-squared, you could have also used the table. You're not going to have Excel on the test, so if there's a gamma distribution that you could recognize as a chi-squared, probably wouldn't you use the table. Okay. And that's if your theta is 2, right? And you have the r over 2. So Alex was just asking about the property of the gamma function that says if you have gamma of alpha, that's alpha minus 1, gamma of alpha minus 1. So that says that if n is a positive integer, now actually if n is just a non-negative integer, but we'll say a positive integer, gamma of n is n minus 1 factorial. And we also noted before that gamma of a half is square root of pi. So for just to use this as an example, if I asked you to compute gamma of 3 halves, what would you tell me that is? Well, so I want to use this property here. Okay, I agree with the gamma of 1/2. What's alpha? What's alpha? What's alpha? 3 halves. What's 3 halves minus 1? 1/2. There we go. So this would be 1/2 root pi, for example.
So gamma of 3/2 is actually smaller than gamma of 1/2?
Yes. Mm-hmm. Part of the reason for that, gamma of 1/2 has this asymptote going this way, versus gamma of 3 halves actually comes up like this. Because when you put 1/2 in for alpha, you get an x to the negative 1/2. So you get that vertical asymptote at 0. So that's why you get some extra area in there. These are not drawn to scale. In fact, they could cross for all I know. I just know that this one doesn't have an asymptote and goes to 0. The other one has an asymptote on it. That's why. It traps some more area. I know it's weird. That's the only one it does it for. The rest of them will all get bigger.
Yeah.
The rest of them will all get bigger because they're all bigger than 1 when you put them outside it, when you do that product. So it'll get bigger every time. But that one actually does get smaller for the first one. It's a weird thing. So it keeps me interested in math, though, is the weird things. It's true.
Wait, with gamma,
All right. We okay with gamma chi-squared? Know how to read the chi-squared table? How to get your probabilities? Those kind of things? Yes.
Like, in the problem, is it told to us, like, what one you use? Like, I'm just trying to remember.
So if you had, let's say I just pull up the chi-squared table here. So let's say you had, I'm just going to pick one out here. Let's say you were asked, let's say you were given this PDF. Say you were given that was your PDF, and you were asked for the probability that x is greater than 32.01. So the first thing, if I've got something weird like this, that's definitely not a normal distribution. So it's going to be chi-squared. If I'm going to have something that's that weird, I'm certainly not going to ask you to do integration by parts on that, and it's not going to help anyway, because at some point you're going to get stuck. Okay? It's going to be when you get to the 1/2 power here, you're going to get stuck. So I'm not asking you certainly to do this by parts, and I don't know why that got so thick as far as the ink went on that one. That's a 21, that's a 23. Eat both of those are 23. So instead, you need to recognize this as a chi-squared distribution. If I'm recognizing this as chi-squared, how many degrees of freedom are there? 23. It's the numerator here, right? So even if I would have done, say, 12 in there, it would be 24, right? Because you have to, it's double, essentially, whatever's inside there. Okay. All right, so 23 degrees of freedom's here on the table. I want this probability, so I need to go find 32.01 on the table. You see it in that row? Hey, shockingly enough, I cheated and looked. There it is, 32.01. So I scroll up. I see 0.9 here, but that's the left tail, right? The 0.9? So what would this be instead? 0.1, yeah. Everybody see why that's the case again? So what did I do again? I recognized the number of degrees of freedom. I went to that row, found the value in the row, and found the corresponding left tail probability, and then subtracted it from 1 to get the right tail. Yeah, Sam?
What do we do for those problems where it's like x is in between two values?
then you would do your two left tails and subtract them. So for this one, if you said I wanted the probability that let's say 13.09 is less than x is less than 41.64. Here's 41.64. Here's 13.09. So I would go up to the top. The 41.64 is 0.99. And I think the 13.09 was in the third column here. So 0.05. So you would go back down here. And you would go back down here. Seriously? One more time. Stay. This would be 0.99 for the 41 point, whatever that was, 64, 04. I can't read my handwriting at this point. And then minus the 0.05 for the second one, and subtract. That makes sense? Okay. That's how you use the chi-squared table for those. And it's also how you use the chi-squared table when we did the normal distribution problems as well. So if I go back over here. Oops. So for 3.6, that was our normal distribution. Yeah.
For what betas for those two, did you say that at some point lambda was equal to like 1 over beta, or the other way around? Beta was equal to 1 over lambda?
For the Poisson to the to the waiting time? Yep.
Is beta equal to 1 over lambda?
They're equivalent. Both things that you said were exactly the same. That's not, well, if that's one. All right. So your normal distribution PDF looks like the following. So your mean, I mean, it's given to you, right? It's written as mu and sigma, isn't it? So the mean is mu and the variance is sigma squared. They write the mean and the variance in the normal distribution PDF. And then your moment generating function is an exponential. The important thing to remember is that that coefficient on the t squared is not the variance, it's half the variance. Right? It's sigma squared over 2. So if you've got a 6 t squared in that exponent, the variance is 12, not 6, is what I'm saying. Okay? So be careful with that. If I gave you some problems in the homework that had moment generating functions given to you, right? And you had to pull out the mean and the variance. Remember, when you pull out the variance, you got to double that coefficient on the t squared. Okay? It's an easy mistake to make. That's why I'm pointing it out. Okay? All right. So again, doing problems with the table using our doing our z-scores, right? So it converts a normal distribution of mean, mu, and variance sigma squared to the standard normal, right? We did problems like this in homework, correct? Okay. And then you had your cumulative distribution function. So that was what the capital phi function represented. And that was where we used the normal distribution table to do the probabilities. Remember those? And then one of the properties that we know is that if we have a standard normal, what happens when you square it? What kind of distribution do you get?
I squared 1.
Good. So that's another type of problem that I could ask you were to go use the chi-squared table, is to ask you to find a probability involving a square of a normal variable. You had ones like that in your homework too, right? Are we comfortable using the table with normal distribution? I'm not going to ask you to interpolate anything, so round your z-scores to 2 decimal places and just look it up in the table. You don't have to do any linear interpolations to go in between values. Just round it to 2 decimal places. Don't round to 1 decimal place. Round to 2 and use the table correctly. Yeah, Marshall.
I was, for that z-square, we're just using that z-score we first calculated, right?
For the z-squared, yeah, it's going to be the distribution. So a lot of the problems will be like, if you start with an x and a mu squared and a sigma squared, it'll be like, what's the probability that x minus mu quantity squared is less than some number?
Right.
That's how it'll be set up, and then you'll just have to convert it. You have to divide both sides by the variance so that you have a chi-squared.
Right.
Yeah.
The huge right parentheses.
It's even bigger now. All right, is it okay? All right, 4.1.
Wait, what about that negative z thing?
About negative z thing.
So like, I circle negative z for 1 minus.
Oh, this one? It's just, it tells you how to read the table by going that way. Yeah, that's just another property to be able to use your table if you've got a negative z-score. So section 4.1 started talking about joint distributions. You should be comfortable doing marginals and expected values and those things of discrete as well as continuous distributions. All right, so you should be able to do expected values using discretes as well as continuous distributions, just as a matter of summing up over things as opposed to integrating, right? We had some problems in homework like that. Being able to compute your marginal distributions, I think that was in this section as well. But of course, we've done marginal distributions in the conditionals as well. So we've been continuing to do marginal distributions. All right, so I think in this section was both expected value and marginal distributions, as well as just computing some good old-fashioned probabilities, right? Honestly, I think, personally for me, I think the most difficult part of these particular problems, especially when you're doing probabilities, is getting your support, your region set up correctly that you're doing your double integral over. You probably noticed that from calculus. Right? Figuring out what you're integrating over is typically the hardest part. Not the actual integration. So make sure you're comfortable setting those things up. 4.2 was covariance. So just to remind you the formula, oops. It's the product of the two variables minus the product of the expected values of the individual variables. So expected value of the product minus the product of the expected values. Whatever those variables happen to be. Right? The letters are x and y, but you could have constants in there, right? You could have an x and an ay, and then you could just multiply it with the a times xy and expected value of x and expected value of ay. Literally, it doesn't matter what the variables are, right? It just gets plugged into those formulas, right? Literally, doesn't matter what the variables are. We also had our formula for correlation. So it was the covariance divided by the product of the standard deviations. We recognize that, this is one of the big things we talked about, that the correlation also has to be always between -1 and 1. This is an important fact for one of your homework problems, One of your homework problems asks what the smallest value is for the variance of x plus y. So you need to know how small can the covariance get. And it's dependent on how small your variance or your correlation can get. Okay? So if you haven't looked at that problem yet, that's important in that one. Okay? Because in that problem, you know your standard deviations. You know how small the correlation can get, so you can get how small the covariance can get. Okay? So that was important. Least squares line was in this section. Scroll, thank you. Just fighting with that and forgot what I was going to say. Oh, I know what it was. When you have the variance of a linear combination of x and y, bless you. I think you have a problem. Well, this is involved in the same problem that is in the I just mentioned above.
Is this going to be our last?
Test before the final?
Yeah.
Yes. Yep. And then also, there's an important thing that we haven't spent a lot of time on, but it's also an important concept. If x and y are independent, that implies that the covariance has to be 0. And in particular, the reason for that is that if x and y is independent, what can I do with this expected value for the product? I can break it up. If they're independent, I can break up the expected values. That just turns out to be 0. Okay. However, the converse of this statement is not true. Just because the covariance is 0 does not imply that x and y are independent. Or independent. Couldn't spell last hour either. Basically, covariance is a measure of linear relationship. If you've got a relationship that, say, is symmetric about the y-axis, that's going to give you a covariance of 0. If it's perfectly symmetric about the y-axis, you have no linear relationship there. But they're still not independent of each other, right? Because you have a perfect quadratic relationship. Okay? So one way is true, the other way is not necessarily true. So that's a concept that's popped up. Yes?
So if it asks us if two variables were independent, how do we prove that?
That's how you have to prove that you can write the joint PDF as the product of the marginals. So you'd have to calculate the individual marginals and multiply it together.
Okay.
To show that they're actually independent. To show that they're dependent, you would just need to find two values for the marginal distribution. When you multiply them together, it doesn't give you the value for the joint. Okay. Section 4.3 was conditional distributions. So the big thing of that, of course, was being able to find the conditional PDF by dividing your joint PDF by the marginal. And you can obviously flip x and y. If I flip it to make x given y, what do we divide by instead? The marginal for y, right? It's always the given part that goes in the denominator, just like what we did before. Yeah, Morgan.
Okay, so is that the same with the expected value?
Yeah, but see, it's the expected value, you would multiply by the x then. Yeah.
Okay.
Yep, instead of the y. But that's the big thing for the conditional distributions, is being able to use that formula correctly. What I would encourage, if you're asked to, say, find the probability of whatever it is, given, say, x is equal to a value, whatever the value happens to be, I just picked a 2. What I would do first is find your g of y given x for an arbitrary x, before trying to plug something in. Okay? You are going to plug in x equals 2, right? At some point. Okay? But don't do it first. The reason I say that is that you can get confused because I have to do some integration things, and I'd rather leave my variables the way they need to be while I do my integration things, making sure I don't plug up a constant in that I don't end up integrating. Okay? I'm not saying that you can't keep it straight. I'm just saying I personally think it's easier to keep it straight, to find your conditional in terms of an arbitrary x first, then plug in the x before you find your probabilities. That's just my personal take. What's that? Stop sign?
Oh,
gotcha. Any questions at all on anything? Yeah, Morgan.
For the variance of AX plus BY,
Mm-hmm.
you talked about one of the plus C, or there's like.
If there was a constant on there, yeah.
Or like, no, like if there's 3 variables.
Oh, if it's 3 variables, you'll get, basically it's the same extension of that. You'll have an a squared variance of x, a b squared variance of y, and a c squared variance of z. And then you'll get the combos. So you get a 2ab covariance of xy, a 2ac covariance of xz, and a 2bc covariance of yz. It's just it's basically 3 choose 2. Okay? I'm guessing it'd be a lot more likely to have 2 than 3.
What's
If that's any kind of a hint.
what time is this study session?
Haley, what time is your study session?
Yeah, don't forget, there's a review session from 7 to 9 in C140 tonight.
Haley, can you text me to remind me that?